Okay, if you have any question, you can just ask me. Okay, our next topic is numerical method. Okay, for ENG topic 5. So this is the topic reference. So based on two books, which is the Modern Engineering Mathematics and also Advanced Modern Mathematics. Okay, especially on Rush Kutai. Okay, this is the topics. 5 numerical method. First is the Euler method, which is you can refer in the modern engineering books at the particular page, and Ranshkita in Advanced Modern Engineering Mathematics in 2.3.8, page 141. Then is a theorem, Taylor's theorems, 9.4 in modern engineering and engineering application in advanced modern books. Okay, Euler. Okay, Euler is the concept of direction fields of differential equation has been given in ODE. Okay, so it's a noted solution of differential equations which is in the curve of t and x plane, to which the direction fields line and tangential of every point. So it suggests that a curve represents the solutions that can be obtained by sketching on the direction field a curve that is always tangential to the lines of directions. So in figure 10.8, so it shows the curve. Okay, this is a okay, this is the example of construction numerical solutions. Okay, so if you can see, this is, for example, this is the main curve. So Euler is on how to calculate the solution on each particular point. So to get the tangential of the line at the particular line. So for example, so starting at point T node X node. So this is okay, T node X node. This is T node X node. For example, we start from here. So a straight line is gradient equal to the value of direction of f function of T node X node is drawn. So the line is followed to a point of abscissa of T node H plus H. So the ordinate of X node plus H of function Tx node, which we shall call x1. So you can see we start with T node X node. So the second point will be in term there is a distance of H constant. Okay, H constant. So in order to get the vertical, so it's a H constant times with the function of T node X node. So you will get a point over here, and you can get the tangent line here. Okay, so the value of direction field at this new point is calculated. Okay, there's a new point which is H F T node X node, and another straight line from this point with a new gradient is thrown. So that's why this new gradient is thrown here. So this one we call it as T1 X1. So this is the new gradient, we call it as a T1 X1. So this is a gradient between of T node X node until of H, which is the distance of H of the function X T node X node. Then we can call it a X1 and T1 as the gradient. Okay. So the line is followed as far of T node to H, and the process can be repeated of any number of times, and curve of Tx consists of number of short straight line segment in the constructions. So if you want to find the second one, for example, this point, another point here. So there will be a maybe 2H. Okay, maybe a 2H here. So your function of this point will be H of 2H lah. Okay, 2H of F T node X node. Okay, so you will find a new function of X2 T2 X2 of the tangent. Okay, so the curve is completely defined by the point in which the line segmentation join, and these can obviously be described by the equation of, okay, for example, you have a T1, which is the T node, the original initial, plus the H. Okay, so the function of x1 is the x node is the first functions, plus H is the distance just now, H, the perkali, or even the scalar, okay, of the function f T node x node. So for T2, okay, the T2, so it's a T1, okay, T1 plus H. H is a time step. For example, you have a each of time step of H equal to 0.1. So this one will be T node plus 0.1. Okay. For example, T node, you start with 0 and 0 plus 0.1. So automatically your T1 will be 0.1. Then for T2 is 0.1 plus this one H 0.1. Okay. So this one will be 0.2. So it's a time step. Okay. So in terms of function x also, it will affect it. Okay. Based on here, for example, you get the first function x node plus the h for the function. Then for x2 is x1, this one, plus the time step of the function. Okay. So then this one it keep repeating in order until you finalize the final point. So this define mathematically the simplest method for integrating the first order differential equation. So we call it as a Euler method. So this called as a Euler method. So solution are constructed step by step. Okay, starting from some given point. Okay, this is the origin point, T node, X node. For a given T node is different, and X node will be give a rise for different solution curve. So this start with T node X1 is the initial, then it keep on increase with T1, T2, X1, X2, and the rest. So these curves are all solution of differential equation, but each corresponds to different initial conditions. Okay, so the solution curve constructed using this method are obviously not exact solutions, but only approximation to solution, because there are only tangential of the direction, field, and certain point. Okay, so between this point, the curve are only approximate, so because this is called approximation, because of it calculate based on the tangential, okay, of that curve line. Okay, you can remember just now, it's a curve line here. So we take a tangential of this area. So it's a tangential of this area. So this one. So this one is the tangential of this area. So it's approximate tangential. So so we expect that as the distance for which we follow each of the straight line segments is reduced, the curve via construction will become better and better. Okay, the smaller of the h, okay, the increment of h in the independent variety along each straight line is called step size. As I mentioned just now, h we call it as a step size. Okay, for example, the step size of 0.1, so it becomes 0.1, then 0.2, keep on increasing 0.3. If your step size is 0.05, it becomes 0.05. So then 0.1, 0.15, and the rest. So this is a step of calculation, step size. So in figure 10.9, three approximate solution of initial value. So for example, you have a function dx over dt is x squared t exponent negative t when your x is 0. So the answer is 0.9. So for the step of size of h, so you have several steps. For example, 0.01, 0.025, 0.0125. Okay. So, okay, these steps are sufficient small that the curve, despite being composed of series of short straight line, give illusion of the smooth. Okay, the smallest of the h will produce a better or accurate of the calculation. So in equation 10.2 actually has an analytical solution. So from here, okay, dx over dt, when we integrate, you get this x value. Okay, so the analytical solution of initial problem is shown as a 10.9 for comparisons. Okay, if you can see here, okay, for examples, this is your function dx over dt, okay, equal to x squared t exponent negative t. So when you integrate this one, you will get the x value, which is this one. Okay, then when we do the time step of h. Okay, we plot it in with different time step of h. You can see that the smallest of time steps produce a nearest value of analytical solution. This is your analytical solutions. So when use 0.0125, the result will be much nearer, okay, much accurate compared to the 0.05. So this figure shows that the smaller h value, okay, smaller h value produce a nearest of the analytic solution. Okay, so in order for you to calculate a very details, you need to reduce the time step. Okay, okay, we go for example. Okay, so for example, the function of xt satisfies the differential equation. So this is your equations, okay, dx over dt is equal to x plus t divided by xt. So we know that initial conditions of when x t1, okay, x t equal to 2, when x is 1 is equal to 2. So this is your initial conditions. So use the Euler method, okay, the question, to obtain an approximation of x2 when x t is equal to, when using the step of h equal to 0.1. Okay, what you need to do now here, we know that our function is dx over dt is equal to x plus t divided by xt. So what you need to do, you need to create your t. Okay, okay, you need to create your t. So this is the t. So we start with the first one. When t equal 1, the answer is 2. So when t equal to 1, your x value is 2. Then you calculate the x plus t, which is x is 2. Okay, this one is 2 plus 1. Okay, you get 3 here. Then xt, which is 2. Okay, 2 times 1 equal to 2. Then you need to calculate the time step. So here we know that the time step is 0.1. H is 0.1. So the next column is a h 0.1 times this function. So here will be h is a 0.1 times what is x plus t is 3 divided by xt is 2. So you will get this one. Okay, this is for initial condition. Initial condition. Okay. Next, we know that h is equal, time step is equal 0.1. So now the second one, okay, the second one will be add up 0.1 become 1.1. Okay, 1.1 here. Okay, 1.1. So what is x? X is you need to calculate x again lah. So in this case, when t is 1.1, your x will be 2 plus 1.15. So this one plus the x, so 2.15. So x plus t is 2.15 plus 1.1, you get 3.25. xt is this one times this one, you get 2.365. Then you calculate the increment of h of 0.1 times x plus t divided by xt. So you get 0.1374. Okay. So then the next is, this next time step become 1.1 to become 1.2. So the value of x is based on additional of the previous x, which is 2.15 plus this one, 0. This time step effects. So you will get 2.2874. So you get here. Then you start again x plus t, xt, and find the steps of the function answer. So then this one plus this one, you get the next of 1.3 and the rest until the answer requires you to get x2. So you calculate until 1.1, 1.2, 1.3, until 1.2.0. So you will get your x value is this value, 1.9 value x plus the times the x, you get 3.1162. Okay, so this is the concept of Euler method. which is in order for you to calculate what is the correct answer of the functions when x equal to with the time step, okay, different time step. Okay, for example, I change it, the time step become h equal to 0.05. So your h here is not 0.1, it becomes 0.05. Then your answer will be changed. Okay, so change, then time step will be 1. Instead of 1.0 to 1.1, it become 1.0 to 1.05, then 1.10, 1.15. So all these calculation will get a different x value. So the smallest h will produce a more accurate results. Okay. So this is on how the Euler method functions. Okay. If you can see here, this is the equation of function. This is the main function, which is I already explained to you just now. Okay. So it's a x1 is an x node. Okay, the original one, initial, plus h, the time step, times the function of t node x node, the original one. So in this case, x node plus h. So what is your function of h is the time step times the function of ft. So what is your function is x plus t divided by xt. So x node plus t node divided by x node t node means the initial. So we start with the x node is a 2. Okay, just now. Okay, we start x node is a 2 plus what is the h? H is the time step is a 0.1. So this is h. Okay, then x node plus t. Okay, back here, what is x node plus t is 2 plus 1. So that's why you can see here 2 plus 1 divided by x times t. So what is x times t? 2 times 1. This is I mentioned just now, 2 times 1. So you get 2.15. Okay, so this is the value of x1. So 2.15 here, the value of x1. So in order for you to get the t2 increase from 1.1 to increasing of h of 0.1, it become 1.2 here. So then the next for value is the previous value x1, which is 2.15, okay, plus what is h? Our time step h is 0.1. Okay, what is x1? X1 is the previous value of x1, which is 2.15, plus what is the previous one is t1, 1.1, divided by 2.15 times 1.1, you will get 2.287. So this is on how you get 2.287, okay? So this is on how you want to calculate the approximation of calculations, okay, using Euler method. So the rest of solution is obtained by step, as mentioned in figure 2.6. The approximation of x2 is at the end is 3.1162. Okay. Okay, so this is the, we have introduced you Euler method via institution of argument from a geometrical understanding of our problems. So Euler method can be seen as an analyze as an application of Taylor series. Okay, the Taylor series given section of 9.4.2 based on the figure. So this is the Taylor series of xt plus h equal to xt, the first function, plus h, the time step size, and the dx over dt. So plus h square 2 factorial d square x over dt square plus 3 h3 3 factorial 3 and the rest. So by using this formula, given the value of xt, all of derivation of x and t, we can compute that x equal to t plus h for any given h. If we choose a small value of h, the Taylor series truncated after finite number of terms will provide a good approximation. As mentioned, small value of h produce a good approximation value of x t plus h. So Euler method can be interpreted using the Taylor series truncated after the second term of approximation of x t plus h. So in order to distinguish between the exact solution of a differential equation and numerical approximation to exact solution, it should be appreciated that all the number of solution, however accurate and only approximate to exact solution, we shall now make explicit the conventions that we use in the last section. So the exact solution of differential equation will be denoted in the lowercase letter. So the Taylor series based on the Euler method can be simplified something like this lah. So x when t plus h equal to xt plus h, the time set dx over dt equal to xt hf xt. So this one is a function of h times a. Okay. Okay. So by applying the Taylor series,